The universe is stranger than we ever imagined. Out there, beyond the familiar worlds of our solar system, orbit planets that defy everything we thought we knew about how worlds could form, how they could behave, what they could be made of. These are not the rocky spheres and gas giants we grew up learning about. These are worlds where glass rains sideways at speeds that would make a jet fighter look slow. Planets made of diamond, worth more money than exists in the entire global economy. Worlds darker than coal, absorbing light like cosmic black holes. Places where rubies and sapphires drift through alien skies, where iron falls as rain, where ice burns hotter than boiling water. Hello there, and welcome to this journey through the stars. Before we venture into the depths of space, I wanted to extend a warm greeting to you, dear listener. Whether you're nestled under the covers, gazing up at the night sky through your window, ready to drift off dreaming of distant worlds, or simply looking to escape Earth's gravity for a while with some quiet astronomical storytelling, I'm so glad you've chosen to join me on this voyage tonight. If you don't mind, I'd love to know where in the world you're tuning in from and what time of day or night it is for you right now. Feel free to leave a comment and let me know. It's always such a delight to see our community of space enthusiasts gathered here from every corner of our small blue planet. And if you enjoy these calm, immersive tales from beyond our world, go ahead and click that subscribe button so you don't miss our next cosmic adventure. But for now, let's allow the stresses of our everyday lives to melt away as we travel outward, far beyond our familiar solar system, to worlds that challenge everything we thought we knew about the universe. For most of human history, we knew of only the planets in our own solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. We assumed, if we thought about it at all, that planets around other stars would be similar. Perhaps a bit larger or smaller, maybe orbiting closer or farther from their suns, but fundamentally the same kinds of worlds. We were wrong, spectacularly, wonderfully wrong. The first planet orbiting a sun-like star beyond our solar system was discovered in 1995, and in the decades since, we've found thousands more. With each new discovery, our understanding of what's possible has been challenged, expanded, and sometimes completely overturned. The planets we've found are so bizarre, so extreme, so utterly alien, that they forced us to rewrite the rules of planetary science. Some shouldn't exist according to our theories. Others exist in conditions so hostile that they challenge our very definition of what a planet can be. This is the story of the most extraordinary worlds we've discovered, places that seem more like science fiction than science fact, yet they're out there orbiting distant stars, waiting to teach us that the universe is far more creative and far more strange than we ever dared imagine. Let's begin with perhaps the most terrifying weather in the known universe. Imagine a world not too different in size from Jupiter, orbiting a star roughly 63 light-years from Earth. At first glance, if you could somehow observe it from a safe distance, it might even appear beautiful. The planet glows with a striking deep azure blue, reminiscent of Earth's oceans seen from space. It's one of the few exoplanets whose color we've actually determined. That brilliant blue might make you think of water, of tropical seas and island paradises. You would be catastrophically wrong. The planet is called HD 189733b and is a hell beyond imagination. The blue color doesn't come from water but from the planet's atmosphere, which contains silicate particles, essentially microscopic fragments of glass. The temperature on this world averages around 1,700 degrees Fahrenheit, hot enough to melt glass into a liquid, hot enough to vaporize silicates into the atmosphere where they condense into tiny, razor-sharp particles that drift through the air like a demonic snow. But temperature isn't the worst part. One side of this planet perpetually faces the blazing sun, while the other side remains in eternal darkness. This creates a colossal temperature difference between the day side and night side, driving winds of unimaginable ferocity. We're not talking about hurricane-force winds. We're not even talking about tornado winds. The winds on this world howl at speeds up to 7,000 kilometers per hour, that's nearly 4,350 miles per hour, or about 7 times the speed of sound on Earth. To put that in perspective, the fastest winds ever recorded on Earth during the most powerful tornadoes might reach 300 miles per hour for brief moments. The jet stream, that river of air that commercial aircraft ride to save fuel, flows at perhaps 200 miles per hour at most. This planet's winds are more than 20 times faster than that, approaching Mach 7. A commercial airliner cruises at about 575 miles per hour. These winds could carry that airliner or obliterate it at more than 7 times its maximum speed. And remember those microscopic glass particles suspended in the atmosphere? They're not gently drifting. They're being accelerated to these incredible velocities, transformed into what amounts to a perpetual sandblaster moving at hypersonic speeds. Except instead of sand, it's glass. Instead of a control tool, it's a planet-wide storm that never ends, that has raged for millions or billions of years and will continue long after our sun has burned out. If you could somehow survive the heat, if you could withstand the pressure of the atmosphere, if your spacecraft could maintain its position against those horrific winds, you would be flayed. The glass particles, moving at hypersonic velocities, would tear through any material we know how to make. Metal would be stripped away in seconds. Diamond might last minutes. Nothing could withstand this assault for long. You would be shredded down to atoms, and those atoms would be scattered across the planet, another layer of dust in the endless storm. The planet sits incredibly close to its star, completing an orbit in just 2.2 Earth days. It's what astronomers call a hot Jupiter, a gas giant that orbits far closer to its star than Mercury does to our Sunday. At that distance, the stellar radiation is intense, heating the planet to those extreme temperatures and driving the formation of those glass clouds. The proximity also causes extreme tidal heating, where the gravitational pull of the star flexes the planet slightly, generating additional heat through friction in the planet's interior. The very existence of hot Jupiters like this one came as a shock to astronomers when they were first discovered. Jupiter-sized planets aren't supposed to form that close to their stars. The intense heat and radiation near a young star should prevent gas from condensing into a giant planet. These worlds must have formed farther out, where conditions were cooler and then migrated inward through interactions with the protoplanetary disk or with other planets. This migration process could take millions of years, with the planet spiraling slowly inward until it reaches a stable orbit close to the star. In recent years, scientists have even detected hints of water vapor in the atmosphere, along with carbon monoxide and other molecules. But don't let the presence of water fool you. At these temperatures and pressures, water doesn't exist as a liquid. Its superheated steam, mixed with the rest of that hellish atmospheric soup blown sideways by those devastating winds, mixed with shards of glass in a storm that defines the word apocalyptic. This is a world that pushes the boundaries of what we thought possible. A planet that looks beautiful from a distance but reveals itself as one of the most hostile environments imaginable once you look closer. A reminder that in the universe, appearances can be deceiving, and that nature has no obligation to make things comfortable for life as we know it. The glass rain planet is a testament to the universe's capacity for violence, for extremes, for conditions so savage they seem impossible, yet there it is, orbiting its star, blue and deadly and utterly alien. From that world of glass and wind, we travel to a planet that sounds like something from a treasure hunter's wildest dream, but the reality is far stranger than any fantasy. If there's one planet that captures the imagination more than any other, it might be this one. 55 Cancri E, a world made largely of diamond, orbiting a star just 40 light-years from Earth. When scientists first analyzed its composition and structure, they realized something extraordinary. This isn't just a planet with some diamonds in it. This might be a world where diamond is one of the primary constituents, where carbon has been compressed under such extreme pressure and temperature that it has crystallized into the hardest, naturally occurring substance we know. Let's start with the basics. This planet is roughly twice the diameter of Earth, but about 8 times more massive, making it a so-called super-Earth, a category of planet that doesn't exist in our solar system but appears to be common elsewhere in the galaxy. It orbits terrifyingly close to its star, completing a full orbit in just 18 hours. To put that in perspective, a year on Earth is 365 days. A year on this world is less than a single day on Earth. The planet is so close to its star that its surface temperature likely exceeds 3,900 degrees Fahrenheit, hot enough to melt iron. At that temperature, you might think diamonds would be impossible. After all, diamonds are formed in Earth's mantle under specific conditions of temperature and pressure. Too hot, and carbon would exist in other forms. But here's where the physics gets interesting. The planet's interior pressure is so extreme, so utterly beyond anything we can easily comprehend, that carbon is forced into its most compact form, diamond. The planet may have a thin crust of graphite, or even molten silicates on the surface, but beneath that, scientists theorize there could be a thick mantle of diamond, perhaps thousands of miles deep. Think about that for a moment. Diamond, which on Earth is rare and precious, existing only in small deposits formed under specific geological conditions, could make up a significant fraction of an entire planet. We're not talking about diamond veins or diamond deposits. We're talking about a diamond layer that could be larger than Earth itself. Compressed and heated to unimaginable degrees, but remaining solid because the pressure is so intense that the carbon atoms have no choice but to pack themselves into that characteristic crystal lattice. This creates extreme temperature differences. The day side, baked by the nearby star, could be hot enough not just to melt iron, but possibly to vaporize rock. The night side, never receiving direct sunlight, would be cooler. Though cooler is relative, it's still probably hot enough to glow visibly. The temperature gradient drives massive heat flow from the day side to the night side, possibly creating fierce winds in any atmosphere the planet might retain at such high temperatures. The diamond planet reminds us that the universe is far more diverse than our experience in the solar system would suggest. We live on a rocky planet with an iron core, orbiting at a comfortable distance from a stable star. We have liquid water, a protective atmosphere, and geological cycles that regulate our climate. We think of this as normal, as the natural state of planets, but it's not. It's just one possibility among countless others. Out there are diamond planets and lava worlds, ice giants and super-Earths, planets orbiting binary stars, and rogue planets drifting through the darkness with no star at all. And this diamond world, orbiting its star every 18 hours, surface glowing hot enough to melt iron, interior crushed into crystalline carbon, stands as a monument to the strange and wondrous variety of worlds the universe can create. It's a planet that shouldn't exist according to our early theories of planet formation. Yet there it is, a cosmic jewel box 4 times closer to its star than Mercury is to the Sun, enduring conditions we can barely imagine and challenging us to expand our understanding of what's possible. Then we discovered the darkest planet known to science, a world that defies this assumption so completely that it seems almost impossible, also known as TRES 2b. This planet orbits a star roughly 750 light-years from Earth, completing each orbit in just 2.5 days. It's another massive gas giant orbiting much closer to its star than Mercury is to the Sunday. But what makes this world truly extraordinary is its appearance. It's darker than coal, darker than black acrylic paint, darker than almost any substance found on Earth. This planet reflects less than 1% of the light that hits it. For comparison, black acrylic paint reflects about 3 to 5% of light. Coal reflects about 4%. This planet is darker than either, absorbing roughly 99% of all the light that falls upon it. It's one of the darkest known objects in the entire universe that isn't a black hole. If you could somehow see this planet up close, illuminated by its nearby star, it would appear as a near-perfect black sphere, a hole in space, darker than the void between stars. How is this possible? What could make a planet so dark? The answer lies in the planet's atmosphere and the extreme conditions it endures. The planet orbits so close to its star that its atmospheric temperature exceeds 1,800 degrees Fahrenheit on the day side. At these temperatures, molecules that would normally be gases or form bright clouds exist in exotic forms. Sodium, potassium, and titanium oxide compounds that would reflect light under normal conditions are vaporized and ionized by the intense heat. The atmosphere likely contains vaporized sodium and potassium, which are excellent at absorbing light rather than reflecting it. There's probably also gaseous titanium oxide, which forms at high temperatures and has the peculiar property of absorbing light very efficiently across most of the visible spectrum. Think of it as a chemical that acts like a light sponge, soaking up photons across many different wavelengths instead of reflecting them back. But here's where it gets even stranger. Despite absorbing 99% of the light that hits it, the planet doesn't appear completely black. Observations have revealed that it actually glows faintly with a deep red hue, like a burning coal in a darkened fireplace. This glow doesn't come from reflected starlight, but from the planet's own heat. The planet is so hot and absorbs so much energy from its nearby star that it literally glows with thermal radiation in the red and infrared wavelengths. It's not reflecting light, it's emitting it, heated to the point where it radiates its own feeble light into the cosmos. This creates a paradox. A planet so dark it absorbs nearly all light, yet glowing from its own heat. If you could observe it from a safe distance with the right instruments, you would see this faint ruddy glow against the blackness of space, a dark world made barely visible by its own thermal emission. It would be an eerie sight, unlike anything we see in our solar system. The planet is tidally locked, like many close-orbiting worlds, meaning one hemisphere perpetually faces the star. This creates that extreme temperature difference between day and night. Heat transport from the day side to the night side is inefficient, as revealed by observations of the planet's thermal emission at different orbital phases. The day side gets almost all the stellar energy, becoming a furnace where even exotic refractory materials might vaporize. The night side, receiving no direct starlight and only the heat transported from the day side by atmospheric winds, remains somewhat cooler, though still far too hot for any familiar materials to exist in solid form. The planet also serves as a reminder that our solar system's diversity, impressive as it is, represents only a tiny fraction of what's possible. We have no equivalent to these scorching gas giants in our cosmic neighborhood. Jupiter itself orbits far from the Sun, where it formed in the cold outer solar system. It's cold enough that ammonia and methane form bright, colorful clouds in its atmosphere, creating the bands and storms we see through telescopes. It has a high albedo, reflecting a substantial fraction of sunlight. It's nothing like this dark, hot world orbiting so close to its star that it's been transformed into something almost unrecognizable as a planet. The darkest planet stands as one of the most extreme examples of planetary diversity. A world that absorbs light like a sponge, that glows faintly with its own heat, that exists in conditions so hostile and so alien that it challenges our understanding of how atmospheres work. It's a planet that reminds us that the universe is not constrained by our expectations, that nature can create worlds darker than our darkest materials, hotter than we thought possible, stranger than our theories predicted. And it's out there right now, silently orbiting its star, a shadow against the cosmos, the darkest world we've ever found. If you thought a planet could surprise you with darkness, wait until you hear about a world where the sky itself is made of metal. WASP 76b is a planet where the day side is so hot that iron vaporizes into a gas, rises into the atmosphere like water vapor on Earth, and then condenses on the cooler night side to fall as rain. Not water rain, not even acid rain or methane rain, iron rain. Droplets of molten metal falling from the sky, glowing as they descend, pattering down on a surface we can barely imagine. This isn't science fiction. This is a real planet, orbiting a star roughly 640 light-years from Earth. It's a massive gas giant, somewhat larger and more inflated than our own Jupiter, orbiting extremely close to its host star and completing each orbit in just 1.8 Earth days. The planet's rotation is synchronized with its orbit, one hemisphere in perpetual day and the other in endless night. And the temperature difference between these two hemispheres creates one of the most bizarre weather patterns known to astronomy. The day side of this planet reaches temperatures around 4,400 degrees Fahrenheit, hot enough to vaporize iron and many other metals. To put that temperature in context, it's hotter than most stars' surfaces. Those stars get much, much hotter in their cores. It's hot enough that rocks would liquefy instantly, that most metals would boil into gas, that molecules would break apart into individual atoms. The day side exists in a state of matter that would be unrecognizable to anyone familiar only with Earth's environment. At these extreme temperatures, Iron, which on Earth is a solid that melts at 2,800 degrees Fahrenheit, not only melts, but vaporizes into a gas. Gaseous iron atoms mix with the rest of the atmosphere, joining hydrogen, helium, and other vaporized materials in a superheated atmospheric soup. Think of it like water vapor on Earth. Solid ice can melt into liquid water, and liquid water can evaporate into water vapor, which rises into the atmosphere, cools at high altitude, and condenses back into liquid to fall as rain. The same process happens with iron on this planet, just at monumentally higher temperatures. The fierce atmospheric circulation on this world carries this iron vapor from the scorching day side toward the cooler night side. As the iron-laden atmosphere crosses the terminator, the boundary between day and night, it cools. And when vaporized iron cools below its condensation point, it doesn't condense into a gas or liquid immediately. First, it must cool enough to transition from vapor to liquid. On this planet, the night side is cooler than the day side, though. Cooler still means well over 2,000 degrees Fahrenheit, and in certain altitude ranges, the temperature drops low enough for the vaporized iron to condense into liquid droplets. These droplets form clouds, not the fluffy white clouds of water vapor we see on Earth, but dark, ominous clouds of liquefied metal hanging in the alien sky. And when conditions are right, these iron droplets grow large enough to fall as rain. Picture it: molten metal drops falling from the sky, glowing orange or red from their own heat, descending through the thick atmosphere toward whatever surface exists below. This rain doesn't cool gently like water rain on Earth. Each droplet remains molten, liquid metal at thousands of degrees, falling in a deadly, glowing cascade. The observations revealed something remarkable: strong iron absorption on the day side of the planet, but significantly reduced iron absorption on the night side. The iron was present in the day-side atmosphere as a gas, but it seemed to be missing from the night-side atmosphere. Where did it go? The answer: it condensed and rained out. The iron vapor is transported to the night side, condenses into liquid droplets, and falls out of the atmosphere, removing it from the gas phase. This creates the asymmetry in the observations: lots of gaseous iron on the day side where it's hot enough to remain vaporized, little gaseous iron on the night side where it condenses and rains out. The atmospheric dynamics on this world must be incredible. The temperature difference between day and night drives winds that could reach thousands of miles per hour, though probably not as extreme as the glass rain world we discussed earlier. These winds carry vaporized metals, hot hydrogen and helium, and probably a host of other exotic materials from the day side to the night side and back again in a perpetual cycle. The day side constantly vaporizes material, which is carried to the night side where it condenses and rains out, possibly pooling on the surface or being vaporized again by the heat transported from the day side. The iron rain world reminds us that planets can have weather cycles as alien to us as anything in science fiction. Rain doesn't have to be water, clouds don't have to be water vapor or ice. On worlds with different temperatures and pressures, other materials can fulfill these roles. We know of planets where it might rain diamonds, worlds where methane forms lakes and rivers, places where silicon compounds might form complex weather patterns. The diversity is staggering, and it challenges us to think beyond our Earth-based experience when imagining planetary environments. And somewhere in the depths of space, on a planet we've never visited and likely never will, the iron rain continues to fall. Day after day, year after year, century after century, the same process repeats. Vaporization, transport, condensation, precipitation. The iron rain falls on the night side in glowing droplets, perhaps pooling into metal seas, while the day side bakes under its nearby star, continuously feeding the cycle with fresh vapor. It's a planet-wide machine, driven by temperature differences and atmospheric circulation, creating weather so alien it seems impossible, yet there it is. Proven by careful observation and analysis, another example of the universe's endless capacity to surprise us with its creativity and strangeness. After these hellish worlds, let's visit somewhere that might seem almost familiar, at least, to anyone who's watched Star Wars. It seemed like pure fantasy, an imaginative detail to make an alien world feel truly foreign. Then, in 2011, astronomers discovered Kepler-16b. We found a planet orbiting not one star but two. A real-life Tatooine where anyone on the surface would indeed see two suns rising and setting in a complex celestial dance. This planet, orbiting roughly 200 light-years from Earth, was the first confirmed case of a planet orbiting a binary star system where the planet orbits both stars rather than just one. It's smaller than Jupiter, but larger than Saturn, with about a third of Jupiter's mass. The two stars it orbits are both smaller and cooler than our Sun. One is about 2/3 the Sun's mass, the other only about 1/5. They orbit each other every 41 days, locked in an eternal gravitational waltz. The planet orbits both stars with a period of 229 days at a distance of about 65 million miles from the center of mass of the binary system. This is roughly similar to Venus's distance from the Sun, which might seem like it could be a comfortable, warm orbit. But because both stars are cooler and dimmer than our Sun, the planet receives less light and heat than Earth does. The estimated surface temperature, if the planet had a solid surface, which it probably doesn't, being a gas giant, would be around -100 degrees Fahrenheit. Cold by Earth standards, but balmy compared to some of the frozen worlds we'll discuss later. The discovery was made using NASA's Kepler Space Telescope, which observed the planet transiting across the faces of both stars. This created a complex pattern of dips in brightness. Sometimes the planet blocked the primary star, sometimes the secondary star, and sometimes both stars were eclipsing each other with no planet involved. Untangling these overlapping signals required careful analysis, but the result was unmistakable: a planet orbiting a binary star. The view from this planet would be spectacular and disorienting. The two stars, while appearing close together in the sky from the planet's orbital distance, would be clearly separated. The primary star would appear as a bright orange disk, similar in appearance to our Sun at sunset, but slightly smaller. The secondary star would be much dimmer and redder, perhaps appearing only about 1/5 the diameter of the primary. Together, they would cast double shadows, creating an alien lighting environment unlike anything we experience on Earth. The orbital dynamics would create a complex pattern of day lengths and stellar positions. Because the planet orbits both stars and the stars orbit each other, the stars' positions relative to each other would change throughout the planet's year. Sometimes they would appear close together in the sky, their light combining to create a brighter day. Other times, they would be more separated, rising and setting at different times, creating periods with one sun in the sky and periods with both. There might even be brief moments during certain orbital configurations when both stars would set almost simultaneously, creating that iconic double sunset that inspired the original science fiction imagery. Scientists can use these orbital perturbations to learn about the system's architecture and to test our understanding of gravity in complex multi-body systems. Newton's laws of motion work beautifully for two-body systems, one star and one planet, or two stars orbiting each other. But adding a third body makes the mathematics exponentially more complex. There are no simple equations that exactly describe the motion of three gravitationally interacting bodies. Instead, astronomers must use numerical simulations, calculating the gravitational forces at each moment in time and integrating forward to predict future positions. The planet has probably existed in its current orbit for billions of years, forming either in place from the protoplanetary disk that surrounded both young stars or possibly forming farther out and migrating inward. The migration scenario is complicated in binary star systems because the gravitational interactions can either help or hinder inward migration depending on the specifics of the disk structure and the star's orbital properties. Understanding how planets like this form and migrate helps us understand planet formation in general, not just in binary systems. One intriguing question is whether such planets could host life. This particular world is a cold gas giant, almost certainly uninhabitable. But could a rocky, Earth-like planet exist in a similar orbit around a binary star? The answer appears to be yes, at least in principle. The lighting would be strange, and the seasons would follow complex patterns determined by both the planet's orbit around the stars and the stars' orbit around each other. But there's no fundamental reason life couldn't adapt to such an environment. The real-life Tatooine reminds us that planetary systems can be far more complex and varied than the simple picture we learned growing up in our single-star system. The universe isn't obligated to arrange itself in the neat, orderly fashion we're familiar with. Binary stars, triple stars, even larger multiple star systems exist, and many of them host planets. Each configuration creates unique gravitational environments, unique patterns of illumination, unique challenges for planet formation and orbital stability. And somewhere out there, orbiting two small orange and red stars, this gas giant continues its endless orbit, a world where twin suns rise and set in patterns that would mesmerize any observer. It exists not in fiction but in reality, a testament to the universe's tendency to turn imagination into fact, to create the very scenarios that storytellers dreamed up as the most alien, the most foreign, the most unlike our familiar Earth. The double sunset is real, and it's happening right now on a world we've found and studied and confirmed to exist, proving once again that truth can be stranger than fiction. Now we venture into truly alien territory, to a planetary system unlike anything we've discussed so far. PSR J1719-1438b might be the strangest planetary system of all, not just for the planet itself, but for what it orbits. Forget normal stars like our Sun. This planet orbits a pulsar, the rapidly spinning remnant of a massive star that exploded as a supernova. And the planet itself might be the compressed remnant of a former star, crushed down into a sphere of crystalline carbon so dense that it's essentially a planet-sized diamond. This particular pulsar spins 173 times per second. That means the entire neutron star, with its mass greater than the Sun compressed into a sphere the size of a city, rotates completely more than 170 times every single second. It's hard to comprehend that kind of rotation. A point on the equator of this neutron star is moving at a significant fraction of the speed of light. The centrifugal forces are enormous, and only the intense gravity of the neutron star keeps it from tearing itself apart. Astronomers discovered the planet by detecting tiny irregularities in the pulsar's timing. Normally, pulsar pulses arrive with extraordinary regularity, but this pulsar's timing showed periodic variations. These variations indicated that the pulsar was wobbling slightly, pulled back and forth by the gravitational tug of an orbiting companion. By analyzing the wobble's period and amplitude, astronomers could calculate the companion's orbit and mass. What they found was shocking. The companion orbits very close to the pulsar, completing one orbit in just 2.2 hours. It has a mass slightly greater than Jupiter, about 1.2 times Jupiter's mass. But here's the extraordinary part. The object is extremely dense, far denser than any normal planet. The density is so high that the planet couldn't be made of ordinary planetary materials like rock or iron. Those materials simply can't be compressed to the necessary density, even under enormous pressure. The leading theory is that this isn't really a planet at all, at least not in the usual sense. It's probably the remnant of a companion star, the pulsar's former binary partner. Here's the story scientists have pieced together. This pulsar was once a massive star in a binary system with a smaller companion. When the massive star exploded as a supernova, it left behind the pulsar. The companion star survived the explosion and continued orbiting the newborn neutron star. Eventually, almost all of the companion star's outer layers were stripped away. What remained was the star's core, a dense sphere composed largely of carbon and oxygen, the products of helium fusion in the star's interior. This core, no longer burning nuclear fuel and compressed by both its own gravity and the tidal forces from the nearby neutron star, crystallized into a solid mass of carbon. Essentially, the entire core became diamond. This is the planet or planetary remnant that we observe today, a sphere of crystallized carbon, a diamond the size of Jupiter orbiting a pulsar every 2 hours. The density of this object is estimated at about 23 times the density of water, or roughly 3 times the density of diamond on Earth. This is possible because the pressure inside this object is enormous, compressing the carbon into configurations that don't exist naturally on Earth. The environment near a pulsar is one of the most hostile in the universe. The intense magnetic field and the beams of radiation would be instantly lethal to any life. Even without the radiation, the tidal forces at such close range would tear apart anything not held together by immense internal strength. The diamond planet survives only because it's so incredibly dense and solid. A less dense object, a normal rocky planet, for instance, would be torn apart by tidal forces into a ring of debris. The temperature of this diamond world is difficult to estimate, but is probably quite cold. Pulsars themselves are extremely hot. The surface temperature can be hundreds of thousands or even millions of degrees, but they're also very small, so they radiate relatively little total energy. The diamond planet, orbiting at a distance of roughly 370,000 miles, closer than the Moon orbits Earth, probably receives some heat from the pulsar, but not enough to melt or significantly warm such a massive, dense object. The diamond likely remains solid throughout, perhaps with surface temperatures cold enough to freeze nitrogen or even colder. The economic absurdity of this diamond world makes the other diamond planet we discussed seem modest. This object contains more diamond than could exist in trillions of Earth economies. It's worth more than all the wealth that could ever exist in human civilization. Of course, this is meaningless. You can't mine a planet orbiting a pulsar, and bringing that much diamond to Earth would make it worthless. But the sheer scale is staggering. Scientists have found several other pulsar companions with similar properties, suggesting that this formation process a neutron star consuming its companion star and leaving behind a dense, possibly crystallized core happens relatively often in binary systems where one star becomes a supernova. Each of these systems provides a laboratory for studying matter under extreme density and pressure, conditions that can't be replicated in any laboratory on Earth. The diamond pulsar planet represents an endpoint in stellar evolution, the final chapter in the story of a binary star system. One star exploded, creating the pulsar. The other was gradually consumed, leaving only its crystallized heart orbiting the remnant of its former companion. It's a cosmic fossil, a relic of stellar death and transformation, existing in conditions so extreme that its very existence challenges our understanding of matter and gravity. And it's out there right now, orbiting its pulsar 173 times per hour, a sphere of diamond subjected to intense radiation and tidal forces, the compressed remains of a star that died millions of years ago, in a system so alien that it defies easy comprehension. It's not a planet in any traditional sense, yet it orbits a stellar remnant just as planets orbit stars. It's a diamond larger than Jupiter, yet it's invisible to ordinary telescopes, detectable only through its gravitational influence on the pulsar's timing. It's a reminder that the universe's creativity extends even to death, that even the remnants of stellar destruction can create objects of wonder and scientific fascination. From the crystallized remains of a dead star, we travel to a world that might seem more inviting until you look closer. Science fiction has long imagined ocean worlds, planets covered entirely by water, with no land in sight, where life might evolve in endless depths, never seeing the sky. On Earth, water covers about 71% of the surface, but underneath the oceans lies solid rock, and continents break through the water to create land. But could a planet exist where water goes all the way down? Where there's no seafloor, just an ocean hundreds or thousands of miles deep, gradually transitioning to exotic forms of ice at extreme pressures. GJ1214b, orbiting a red dwarf star only 48 light-years from Earth, might be exactly that. It's a super-Earth, roughly 2.7 times Earth's diameter and about 8 times Earth's mass. It orbits extremely close to its star, completing one orbit every 1.6 days. Despite this proximity, the star itself is a red dwarf, much cooler and dimmer than our Sun, so the planet doesn't receive as much heat as you might expect. The estimated temperature is around 450 degrees Fahrenheit, hot by Earth standards, but cool enough that water could exist in some form. The planet's density is the key clue to its composition. With careful measurements of its size, from transit observations, and mass, from the star's wobble, scientists calculated the planet's average density. That density, about 60% of Earth's density, is too low for a rocky planet with an iron core like Earth. The planet can't be made primarily of rock and metal. It must contain a large fraction of something less dense, and the most likely candidate is water. Scientists' models suggest the planet might have a small rocky core, perhaps a few thousand miles in diameter, surrounded by a massive envelope of water that makes up about 10% of the planet's total mass. For comparison, all of Earth's oceans combined represent only about 0.02% of Earth's total mass. This planet has proportionally 500 times more water than Earth, enough that the water isn't just a thin surface layer, but a thick shell extending hundreds of miles deep. This seems paradoxical, but it's real physics. Under sufficient pressure, water molecules are forced into crystalline structures, ice, even at temperatures where water would normally be liquid. There are at least 18 known phases of water ice, most of which don't exist naturally on Earth but can be created in laboratories at high pressures. On this water world, several of these exotic ice phases probably exist at different depths, forming layers. Superheated steam or supercritical fluid near the top, compressed liquid water lower down, then various forms of hot ice at still greater depths, all sitting atop the rocky core. The discovery of this planet was significant because it represented the first potential water world found outside our solar system. While we have candidates for water-rich worlds in our own solar system, Jupiter's moon Europa and Saturn's moon Enceladus both have liquid water oceans beneath their icy crusts. This was different. This is a planet, not a moon, and its water isn't hidden beneath ice, but makes up the bulk of the planet itself. Could such a world harbor life? The question is fascinating and difficult. The surface environment, with temperatures around 450 degrees Fahrenheit and possibly thick clouds blocking most sunlight, doesn't seem particularly hospitable. But life has surprised us before, surviving in Earth's deep ocean vents, in acidic hot springs, in the frigid Antarctic ice. Perhaps life could exist in the cooler upper layers of the water envelope, or in the interface between different ice phases, or even in the water-rock boundary at the core. One challenge for life on such a world would be the lack of nutrients. On Earth, the ocean's productivity depends partly on nutrients eroded from continents and delivered to the ocean by rivers, and partly on volcanic activity on the seafloor that releases minerals. On a world with no continents, and possibly a rocky core so deeply buried that it can't interact much with the water above, nutrient cycling might be very different. But we shouldn't let our Earth-based assumptions limit our thinking. Life, if it exists on such worlds, would have evolved under conditions utterly unlike Earth and might work in ways we can't imagine. The planet transits its star, which allowed the initial detection and has enabled follow-up studies of its atmosphere. Astronomers have used space telescopes to observe starlight filtering through the planet's atmosphere during transit, looking for absorption features that would reveal the atmospheric composition. These observations have been challenging because the planet's atmosphere appears to be cloudy or hazy, blocking much of the light and making it difficult to detect specific molecules. But the haziness itself tells us something. The atmosphere is thick and filled with particles, possibly water droplets or more exotic clouds. Regardless of whether it's primarily water or has a thick hydrogen atmosphere, this planet represents a class of worlds that don't exist in our solar system. It's larger than Earth, but smaller than Uranus or Neptune, occupying a size range where we have no local examples to study. Super-Earths and mini-Neptunes, as these intermediate-sized planets are called, appear to be common in the galaxy, perhaps the most common type of planet, yet we don't have one nearby to study in detail. Each discovery adds to our understanding of this population. The water world, whether it's covered in oceans hundreds of miles deep or shrouded in a thick hydrogen atmosphere, stands as a reminder of how much we still don't know. We can detect these planets, measure their size and mass, observe their transits, and analyze what little light filters through their atmospheres. But we can't yet determine with certainty what they're really like. Are there waves on those alien oceans? Are there depths where sunlight never penetrates, darker than any place on Earth? Could life swim in those waters, adapted to pressures and temperatures that would crush and boil any Earth organism? These questions remain open, waiting for better telescopes, more sensitive instruments, and perhaps someday missions to study these worlds up close. For now, the water world orbits its red dwarf star, possibly covered in an endless ocean, possibly shrouded in hydrogen, definitely unlike anything in our solar system, and definitely one of the most intriguing planets we've ever found. We've visited hot planets before, but none of them compare to what comes next, a world that makes all the others seem almost pleasant by comparison. Kelt 9b holds the record as the hottest planet ever discovered, with a dayside temperature that rivals some stars. We're talking about a surface temperature around 7,800 degrees Fahrenheit or about 4,300 degrees Celsius. To put that in perspective, our Sun's surface temperature is about 10,000 degrees Fahrenheit. This planet is nearly as hot as the surface of a star. The planet orbits a blue-white star about 670 light-years from Earth. This isn't just any star, it's an A-type star, significantly hotter and more massive than our Sun, with a surface temperature around 18,000 degrees Fahrenheit. The planet orbits this blazing star at a distance closer than Mercury is to our Sun, completing one orbit in just 1.5 days. The proximity to such a hot, luminous star creates conditions on the planet that are almost incomprehensible. At 7,800 degrees Fahrenheit, molecules can't survive. The thermal energy is so extreme that molecular bonds break apart. Water, carbon dioxide, methane, all the molecules we typically associate with planetary atmospheres would be torn into individual atoms almost instantly. The planet's atmosphere isn't made of molecules but of atomic hydrogen, atomic helium, and ions of various heavy elements. It's an atmosphere of individual atoms and electrically charged particles, more like the outer layers of a star than a traditional planetary atmosphere. The heat is so extreme that even metals vaporize. Iron, which melts at 2,800 degrees and boils at about 5,000 degrees Fahrenheit, would be gaseous on this planet. Titanium, with a boiling point around 5,950 degrees Fahrenheit, would also be vaporized. Even tungsten, which has the highest melting point of any pure metal at 6,192 degrees Fahrenheit, would be liquid and possibly gaseous on the day side of this world. Nothing solid could exist on the surface if there even is a surface beneath the thick, hot atmosphere. Like many close-orbiting worlds, this planet always shows the same face to its star. This creates an extreme temperature difference between the day side and night side. The day side, baked by direct stellar radiation, reaches those incredible 7,800-degree temperatures. The night side, receiving no direct starlight, is much cooler, though cooler still means around 6,500 degrees Fahrenheit, hot enough to vaporize most materials. The temperature gradient drives ferocious winds that transport heat from the scorching day side toward the cooler night side. What's particularly fascinating about this planet is that it's being destroyed in real time. The intense heat and radiation from the nearby star are causing the planet's atmosphere to evaporate into space. The outer layers of atmosphere are heated so much that atoms reach escape velocity and simply boil off into space, streaming away from the planet in a comet-like tail of hydrogen and other gases. Astronomers have detected this escaping atmosphere, observing absorption features from the gas streaming away from the planet. The planet is losing mass at an estimated rate of about 10 to 100 million tons per second. That sounds enormous, and it is by human standards. But the planet is so massive, about 3 times Jupiter's mass, that it would take trillions of years to completely evaporate at this rate. The star will die long before the planet completely vanishes. Still, this planet is visibly shrinking, its atmosphere being stripped away and lost to space, never to return. The evaporating atmosphere is enriched with heavy elements. Scientists have detected iron and magnesium in the escaping gas, along with other metals. On the day side, these metals are vaporized and rise into the upper atmosphere, where they're heated further and accelerated to escape velocity. This creates a metal-rich stream of material flowing away from the planet. If you could somehow observe this planet from a safe distance with the right instruments, you might see this tail of escaping atmosphere glowing with the characteristic colors of ionized metals. The hottest planet stands as perhaps the most extreme example of planetary environments, a world where the very concept of surface conditions becomes meaningless because everything is gas or plasma, where atmospheric chemistry is more akin to stellar physics, where the planet itself is slowly being vaporized and lost to space. It's a world that shouldn't exist according to our early theories. A Jupiter-mass planet should have migrated inward early in the system's history, when the protoplanetary disk could provide a mechanism for migration. But it shouldn't have survived this close to such a hot star without being completely destroyed. Yet here it is, clinging to existence, slowly evaporating, a testament to the universe's ability to create conditions at the very edge of what's physically possible. And it's out there right now, orbiting its blazing blue-white star every day and a half, glowing with its own heat, its atmosphere streaming away into space, atoms and ions flowing outward like a stellar wind, marking time until either the planet is stripped down to some denser core or the star itself evolves and swallows it. It's the hottest planet we know, possibly the hottest planet that can exist while still remaining recognizable as a planet. It's a world at the edge, in every sense of the term. From the hottest hell, we now travel to one of the coldest places we've ever found a planet, where the temperature hovers around -220 degrees Celsius, -364 degrees Fahrenheit. Only about 50 degrees above absolute zero, the coldest temperature physically possible in the universe. OGLE 2005 BLG 390LB is a world of eternal, frigid darkness where any atmosphere would have long since frozen solid and fallen as ice to the surface, where even exotic materials like methane and nitrogen exist as ices rather than gases. This planet orbits a red dwarf star roughly 22,000 light-years away, about halfway to the galactic center. The star itself is tiny, with only about 22% of the sun's mass, making it cool and dim, a faint ember compared to our sun's blazing fire. The planet orbits at a distance of about 2.6 astronomical units, slightly farther than Mars orbits our Sunday. If this planet orbited our Sun at that distance, it might be chilly but not impossibly so. Think of a colder, more distant Mars. But because the host star is so dim, emitting only a tiny fraction of our Sun's light and heat, the planet receives almost no warmth. It's a frozen ball of ice and rock, as cold as the depths of interstellar space. This frozen world has a mass about 5.5 times that of Earth, making it a super-Earth or perhaps a small ice giant, similar to a scaled-down version of Uranus or Neptune. The planet's composition is uncertain, but given its mass and the cold environment where it formed, it's likely made of a mixture of rock and ice, water ice, certainly, but also frozen methane, ammonia, and other volatile compounds that would be gases on Earth but are solid at these temperatures. At minus 220 degrees Celsius, the environment is incredibly hostile. This is colder than Pluto's surface temperature, colder than any place in our solar system except perhaps the coldest crater floors at the lunar poles or certain permanently shadowed regions on other moons. Liquid water is obviously impossible. Water ice would be as hard as granite and just as stable. Even gases like nitrogen and methane, which make up Titan's atmosphere and Triton's thin envelope of gas, would be frozen solid on this world. There's almost certainly no atmosphere, or if there is one, it's extraordinarily tenuous, perhaps consisting of whatever few molecules have enough thermal energy to remain gaseous at these temperatures. Hydrogen and helium, the lightest and most volatile gases, might persist as a thin envelope, but anything heavier would have long since condensed and frozen onto the surface. The sky, if you could stand on this frozen surface and look up, would be black and full of stars, no scattering of light by an atmosphere to create the blue sky we're familiar with on Earth. The surface would be a landscape of unimaginable desolation, ice sheets stretching to every horizon, frozen harder than steel. Impact craters from ancient meteor strikes preserved perfectly because there's no erosion from wind or water, no geological activity to erase them. The star would be visible, a dim red point, providing almost no heat, barely brighter than the full moon appears from Earth. Darkness would be the dominant feature, perpetual twilight at best, with long shadows and a landscape illuminated only by starlight and that feeble red Sunday. If you could somehow survive on this world, in a heavily insulated suit with active heating systems, you would find it eerily quiet. Sound doesn't travel well in the near vacuum of a missing or nearly absent atmosphere. Your footsteps would crunch on the frozen ice, but the sound wouldn't carry far. It would be one of the quietest places imaginable, a frozen tomb of a world where nothing moves, nothing changes, nothing lives. This planet's existence tells us something important about planet formation. Planets can form even around the dimmest, smallest stars. The red dwarf hosting this frozen world is barely massive enough to be a star at all, much less massive, and it would be a brown dwarf, unable to sustain hydrogen fusion. Yet even around this barely star, a planetary system formed. This suggests that planet formation is a robust process occurring around virtually all stars, regardless of their mass or brightness. Some scientists have speculated about whether life could exist on such a frozen world. The obvious answer would seem to be no, it's far too cold, there's no liquid water, probably no atmosphere, certainly no sunlight for photosynthesis. But life has a way of surprising us. On Earth, we've found microorganisms surviving in Antarctic ice at -40 degrees Celsius in a state of suspended animation. Could similar organisms exist on this frozen world, perhaps deep beneath the ice where radioactive decay in the rocky core provides minimal heat? Could there be liquid water deep underground, warmed by tidal heating if the planet has a large moon, or by residual heat from the planet's formation? These scenarios seem unlikely, but they're not impossible. The universe has shown us repeatedly that life's requirements might be more flexible than we think. Europa and Enceladus, moons in our solar system, have liquid water oceans beneath their icy crusts, warmed by tidal heating from their nearby gas giant planets. Could a similar mechanism work here? Probably not. The planet likely has no large companion to provide tidal heating, and the dim star provides almost no energy. But we've been wrong before about what's possible. The frozen planet serves as a reminder that not all worlds are hospitable, that the universe contains far more dead, frozen rocks than living, vibrant biospheres. For every potentially habitable planet orbiting a sun-like star at just the right distance for liquid water, there are probably dozens or hundreds of frozen worlds like this one, too far from their dim stars to ever be warm, condemned to eternal winter from the moment they formed. And it's out there still, orbiting its dim red star every 10 years, frozen solid, darker and quieter than any place we know, a world where time seems to have stopped, where nothing happens and nothing changes, where the thermometer hasn't risen above -200 degrees Celsius in billions of years and probably never will for billions more. It's one of the loneliest places we've ever found a frozen hell that's the opposite of the burning hells we've discussed, but no less hostile and no less alien. Our journey now takes us to perhaps the most beautiful sounding planet we'll encounter, though beauty in space is always deceptive. Imagine clouds made of rubies and sapphires, drifting through an alien sky. Imagine winds carrying these precious gemstones from one hemisphere to another, where they rain down in glittering cascades before evaporating again. This seems like the purest fantasy, something from a fairy tale rather than real astrophysics. Yet we've found a planet where this might actually occur, a world where corundum, the mineral that forms rubies and sapphires on Earth, could condense into clouds and rain from the sky. HATP-7b orbits a star about 1,040 light-years from Earth, completing each orbit in just 2.2 days. This enormous gas giant hugs its star so closely that temperatures on the day side reach around 4,900 degrees Fahrenheit, hot enough to vaporize most rocks, but with complex atmospheric circulation that creates cooler regions where exotic materials can condense. On Earth, corundum is aluminum oxide, a hard mineral that forms deep underground under specific conditions of temperature and pressure. When corundum contains trace amounts of chromium, it becomes ruby, glowing red. When it contains iron and titanium, it becomes sapphire, typically blue, though other colors are possible. These gems are among the hardest naturally occurring minerals, rated 9 on the Mohs hardness scale, just below diamond. They're rare and valuable, precisely because the conditions for their formation are unusual. But on this infernal world, the conditions are anything but Earth-like. The intense heat vaporizes aluminum and oxygen into the atmosphere, where they can combine to form aluminum oxide molecules. The atmospheric circulation on this tidally locked planet carries these materials from the searingly hot day side toward the cooler night side. As the temperature drops, aluminum oxide can condense not into the large, well-formed crystals we mine on Earth, but into tiny particles, microscopic or slightly larger, that drift through the atmosphere like dust. These particles are corundum. They have the same chemical composition as rubies and sapphires, the same crystal structure, the same properties. Depending on what trace elements are present in the atmosphere, chromium, iron, titanium, and others, these particles could take on colors. Some might be red like rubies, others blue like sapphires. Still, others might be pink, green, or yellow, all possible colors for corundum depending on its impurities. As these corundum particles accumulate, they form clouds, not the fluffy white water vapor clouds we see on Earth, but clouds of microscopic gemstone particles, glittering and sparkling, drifting through the alien sky. When enough particles accumulate and grow large enough, they fall as rain. Picture it: a rain of tiny sapphires and rubies falling through the thick atmosphere, pulled down by gravity until they reach lower altitudes where the temperature is higher and they vaporize again. The aluminum and oxygen dissociating back into the gas phase to be carried aloft once more. The atmospheric dynamics driving this process are complex. One side perpetually bakes under the star's glare while the other freezes in darkness. The day side is blasted with intense radiation, heating the atmosphere to thousands of degrees. This hot air rises and flows toward the night side at high altitude. On the night side, the air cools and descends, then flows back toward the day side at lower altitudes, creating a circulation pattern. This is similar to the Hadley circulation on Earth that drives trade winds, but vastly amplified by the extreme temperature difference between day and night. As air flows from day to night, it carries vaporized metals and minerals. When the air cools on the night side, these materials condense out, forming clouds of various exotic substances. Corundum is just one possibility depending on the exact temperature and pressure at different altitudes and locations. You might also have clouds of iron, silicates, titanium compounds, or other exotic materials. The night side of this planet might be layered with different cloud types at different altitudes, each composed of different minerals that condense at different temperatures. What would it be like to see these clouds? If you could somehow hover in the atmosphere at the right altitude, protected from the intense heat and radiation, you might see shimmering clouds with a subtle sparkle, different in texture and appearance from any clouds on Earth. Depending on the size of the particles, ranging from microscopic dust to perhaps sand grain-sized particles, if conditions allow growth, the clouds might appear hazy and diffuse or more substantial. The colors would depend on the trace elements present, possibly creating clouds with hints of red, blue, pink, or other hues against the alien sky. The rain itself would be unlike anything we experience on Earth. Individual particles would be tiny, far too small to see individually, but collectively they would create a sparkling mist or drizzle. Unlike water raindrops, which are soft and spherical, falling gently, at least for small drops, corundum particles are hard and irregular, and they would fall faster due to their higher density. If you could hold out your hand, protected, of course, these particles might feel like very fine sand or powder, harder than any Earth sand, composed of a material we consider precious, but here as common as water vapor. But the scientific value is immense. This planet serves as a laboratory for studying mineral chemistry under extreme conditions. On Earth, we can study Corundum formation only in limited contexts in Earth's mantle, where we can't directly observe it, in laboratories where we can only approximate natural conditions, or in rare deposits where corundum has been brought to the surface. On this planet, corundum formation is happening continuously on a planetary scale, and we can observe the results by analyzing the planet's light and spectrum. The Jewel World reminds us that the universe's creativity extends even to weather and clouds. On Earth, we have water clouds and occasional ice clouds. On Venus, clouds of sulfuric acid. On Titan, methane clouds and rain. On Saturn and Jupiter, ammonia clouds, water ice clouds, and complex photochemical hazes. Each world has its own particular brand of meteorology determined by its temperature, pressure, and composition. And on this distant planet, clouds of sapphires and rubies drift through alien skies, condensing and evaporating, raining and rising, in a cycle as natural on that world as the water cycle is on ours. It's a world where precious gems are as common as raindrops, where the very thing humans have valued and fought over for millennia exists in such abundance that it's just another atmospheric constituent, no more special than nitrogen or oxygen are in Earth's atmosphere. It's a profound reminder that value is relative, that rarity is context-dependent, and that the universe contains wonders that dwarf our earthly concerns. Those clouds will continue to form and dissipate, that rain will continue to fall and evaporate long after our civilization has risen and fallen, indifferent to whether any intelligent being ever observes them or assigns them value. They simply are, following the inexorable laws of physics and chemistry, beautiful in their alien way. Just when you think you've seen every contradiction the universe can offer, along comes a planet that defies one of the most basic assumptions we have about matter. Gliese 4.3.6b defies common sense in a way that seems almost impossible. It's covered in ice-solid water ice, like the ice in your freezer, but this ice is burning hot, with temperatures around 800 degrees Fahrenheit. It seems like a contradiction. How can ice exist at temperatures far above water's boiling point? How can something be simultaneously frozen solid and scorching hot? The answer lies in exotic physics that only becomes relevant under extreme conditions, conditions that simply don't exist anywhere in our everyday experience. The planet orbits a red dwarf star only 33 light-years from Earth, relatively close by cosmic standards. It's roughly the size of Neptune, making it one of the few Neptune-sized planets we've found close enough to study in detail. It orbits very close to its star, completing each orbit in just 2.6 days, and this proximity heats the planet to those extreme temperatures. By any ordinary logic, the planet should be completely molten, or even gaseous, at these temperatures. Water should be steam, not ice. Yet the observations clearly indicate that the planet has a substantial layer of ice. The key to this paradox is pressure. The planet has substantial mass, about 23 times Earth's mass, and this mass creates enormous pressure in the planet's interior. Near the surface, where pressure is lower, conditions might be more normal, perhaps a thick atmosphere of hydrogen and helium with temperatures in the hundreds of degrees. But as you go deeper, pressure increases dramatically. Within a few hundred miles of the surface, the pressure becomes so extreme that it changes water's behavior completely. So the planet likely has a layered structure, a rocky core at the center, surrounded by a thick mantle of hot ice, Ice 7, Ice 10, or other high-pressure phases, and then a thick atmosphere of hydrogen, helium, and probably water vapor above that. The temperatures increase as you go inward due to the gravitational compression and residual heat from the planet's formation. But despite the high temperatures, the ice mantle remains solid because the pressure is so enormous that the water molecules have no choice but to form solid crystalline structures. This burning ice concept is genuinely strange and hard to wrap your mind around. We're used to thinking of ice as cold, as something that melts when heated. But under these extreme conditions, ice becomes something different, a high-density solid that persists despite high temperatures simply because the pressure won't allow it to melt. If you could somehow extract a chunk of this ice and bring it to Earth's surface, maintaining its temperature but releasing the pressure, it would instantly flash into steam, explosively transforming from solid to gas as the pressure constraint was removed. This atmospheric escape is changing the planet over time. It's slowly losing its hydrogen and helium envelope, though at its current mass, this process would take billions of years to strip away a significant fraction of the atmosphere. Eventually, in the distant future, the planet might lose most of its light gas envelope, becoming a much smaller ocean planet composed primarily of the water divided by ice mantle with only a thin atmosphere remaining. But this transformation, if it happens at all, will take longer than the current age of the universe. The orbit of this planet is also peculiar. It's slightly eccentric rather than circular, which was surprising for a planet orbiting so close to its star. Tidal forces should have circularized the orbit long ago. The fact that the orbit remains eccentric suggests something is maintaining it, possibly another planet in the system perturbing the orbit. Scientists have searched for this hypothetical companion planet but haven't found it yet, though there are hints in the data that it might exist. The planet's composition tells us something about where it formed. With so much water, even if it's currently in the form of hot ice, the planet must have formed in the colder outer regions of its planetary system, beyond the ice line, the distance from the star, where it's cold enough for water to freeze. Closer to the star, any water would have been vaporized during the system's formation, preventing water-rich planets from forming there. This planet must have formed farther out and then migrated inward, gradually spiraling toward its star over millions of years until it reached its current close orbit. The discovery of this burning ice world has important implications for understanding planetary composition and structure. It demonstrates that water can make up a significant fraction of a planet's mass, even in planets orbiting close to their stars, as long as the planet has enough pressure to keep that water in solid form. This has implications for the study of super-Earths and mini-Neptunes, many of which might have similar internal structures with high-pressure ice mantles. It also provides a reminder that the universe operates under conditions far more extreme than we normally experience. The physics we learn in school, based on everyday pressures and temperatures, represents only a tiny slice of what's possible. At extreme pressures, materials behave in counterintuitive ways. Ice becomes hot, hydrogen becomes metallic, carbon becomes diamond. Understanding these exotic states of matter requires sophisticated physics and careful observation of places where such conditions naturally occur, places like this burning ice world. The planet continues orbiting its red dwarf star, its ice mantle remaining solid despite the heat, its atmosphere slowly escaping into space, a contradiction made manifest, a reminder that nature's rules are more flexible and more strange than our intuitions would suggest. It's ice that doesn't melt. water that's solid despite the heat, a frozen fire that has burned for billions of years and will continue for billions more, following laws of physics that seem paradoxical only because they're so far from our daily experience. All the planets we've visited so far, no matter how extreme, have one thing in common. They'll continue orbiting their stars for billions of years. Our next destination doesn't have that luxury. Most planets have stable orbits that will persist for billions of years, allowing them to orbit their stars until the stars themselves die. This planet is not one of them. This is a world being actively consumed by its star, gradually torn apart by tidal forces and intense radiation, spiraling slowly inward toward inevitable destruction. WASP-12b is a planet with a death sentence, and astronomers are watching its final chapter unfold. The planet orbits a sun-like star about 870 light-years from Earth, completing each orbit in just 1.1 days, one of the shortest orbital periods known. It orbits so close that it's practically skimming the star's outer atmosphere at a distance only about 1.9 million miles from the star's surface. For comparison, the Moon orbits Earth at a distance of about 240,000 miles. This planet orbits its star at less than 8 times the Earth-Moon distance, despite the star being 1 million times more massive than Earth. At this close range, the star's gravity raises enormous tides on the planet. Just as the Moon raises tides in Earth's oceans, pulling the water toward and away from it, the star pulls on this planet, distorting it into an egg shape. But unlike Earth's gentle tides, which raise the ocean by a few feet, these tidal forces are strong enough to distort the entire planet, stretching it along the line, connecting it to the star. The planet is no longer spherical but elongated, with a pronounced bulge pointing toward the star. These tidal forces don't just distort the planet, they tear material away from it. The outer layers of the planet's atmosphere, already heated to extreme temperatures by the star's intense radiation, are being pulled off and forming a stream of material that flows from the planet toward the star. This material creates an accretion disk around the star, similar to the disks that form around black holes or young stars, but in this case fed by a dying planet rather than interstellar gas. The planet is losing mass at an estimated rate of about 6 billion tons per second. That's an almost incomprehensible number. For comparison, Earth's entire atmosphere weighs about 5 quadrillion tons, that's 5 with 15 zeros. At its current rate of mass loss, this planet is losing the equivalent of Earth's entire atmosphere every 23 years. The planet currently has about 140% of Jupiter's mass, so at this rate, it would take about 10 million years to completely evaporate. That might sound like a long time, but it's a blink in cosmic terms. The star is billions of years old, so this process of destruction is happening right now in the star's lifetime. The temperatures on this planet are extreme, reaching around 4,600 degrees Fahrenheit on the day side, hot enough to melt most materials. The planet always shows the same face to its star, creating an extreme temperature difference between day and night. The night side, though still hot by Earth standards, is much cooler than the day side. This temperature gradient drives fierce winds that transport heat around the planet. Observations have revealed something even more dramatic. The planet has a comet-like tail. As material is stripped from the planet's atmosphere and flows toward the star, it doesn't fall directly in, but forms an extended tail stretching millions of miles behind the planet in its orbit. This tail is made of hydrogen, carbon, and other elements, creating a tenuous cloud that's visible in certain wavelengths. When the planet transits its star, this tail passes in front of the star as well, causing additional dimming that reveals its presence. What will happen when the planet finally meets its end? As it spirals closer, the tidal forces will increase, tearing away more and more material. Eventually, the planet will reach the Roche, limit the distance within which tidal forces are stronger than the planet's own gravity, holding it together. At that point, the planet will be torn apart completely, shredded into a ring of debris orbiting the star. This debris will gradually fall into the star over perhaps a few thousand years, temporarily making the star slightly brighter as it accretes the material. For now, the planet persists, orbiting its star every 26 hours, being gradually torn apart but not yet destroyed. It's a world living on borrowed time, a reminder that orbital dynamics aren't always stable, that planets can die not just when their stars die, but through more direct destruction. In our solar system, the planets have stable orbits that should persist for billions of years. But in systems where planets orbit much closer to their stars, especially around stars that rotate slowly, tidal decay can be significant, leading to planetary death spirals like the one we're witnessing here. The doomed planet serves as a laboratory for studying extreme tidal interactions, atmospheric escape, and the final fate of close-orbiting planets. It's also a preview of what might happen to some exoplanets in the future as their orbits decay and they spiral into their stars. And it's a sobering reminder that planetary systems are dynamic, evolving, and sometimes violent places where worlds can be born, live out their existence, and die, all according to the pitiless laws of gravity and orbital mechanics. Every planet we've discussed has orbited a star, even the doomed one, at least for now. But what if a planet had no star at all? It's one of the defining characteristics we associate with planets. They're objects that orbit, held in place by the gravity of their host star, following the same basic rules that govern Earth's orbit around the Sun and Jupiter's orbit and all the rest. But PSO J31 8.5-22 breaks that rule completely. It has no star. It drifts through interstellar space alone, an orphan world wandering the galaxy with no sun to light its days, no star to provide heat, no gravitational anchor. It's a rogue planet, and it challenges our very definition of what a planet is. The object lies about 80 light-years from Earth, floating alone in the constellation Capricornus. It has a mass about 6 to 7 times that of Jupiter, placing it in an ambiguous category between planet and brown dwarf, not massive enough to sustain hydrogen fusion like a star, but more massive than typical planets. Its age is estimated at only about 12 million years, making it extremely young by cosmic standards. For comparison, Earth is about 4.5 billion years old. This object is less than 1% of Earth's age, practically a newborn. Because it's so young, it still retains heat from its formation. When planets and brown dwarfs form from collapsing clouds of gas, the gravitational compression heats them to high temperatures. Over millions and billions of years, they gradually cool, radiating this heat into space. This object is still in the early stages of this cooling process, and it glows with its own heat in infrared wavelengths, with a temperature around 1,800 degrees Fahrenheit at its surface or upper atmosphere. This is much cooler than a star, but far hotter than any planet in our solar system. The infrared glow is what allowed astronomers to discover it. Unlike planets orbiting nearby stars, which we usually detect indirectly through their effects on their host stars, this object could be detected directly because it emits its own light. Infrared surveys of the sky, searching for faint, cool objects, found this glowing world floating alone with no star nearby. Follow-up observations confirmed that it wasn't orbiting any star, at least not within many thousands of astronomical units, if there is a very distant companion. How did this world come to be alone? There are several possibilities, and scientists aren't sure which is correct. Life on such a world would seem impossible. With no star to provide energy, photosynthesis is out of the question. The surface or upper atmosphere is hot by our standards, but only because of residual formation heat, and this heat will gradually dissipate over billions of years. Eventually, the object will cool to temperatures comparable to interstellar space, only a few tens of degrees above absolute zero. Any world can't sustain life as we know it without an energy source. But some scientists have speculated about exotic possibilities. If the object has a thick atmosphere with strong greenhouse effects, and if there are internal heat sources like radioactive decay or residual heat that haven't yet dissipated, there might be warmer layers deep in the atmosphere where temperatures are more moderate. On Earth, some ecosystems in the deep ocean exist entirely without sunlight, powered instead by chemical energy from hydrothermal vents. Could similar chemosynthetic life exist in the atmosphere of a rogue planet, living on chemical gradients and whatever energy sources exist independently of stellar radiation? These scenarios are highly speculative, but they illustrate an important point. We don't fully understand the requirements for life. We know what works on Earth, but the universe is vast and diverse, and life might find ways to exist in environments we consider impossible. The object's composition is uncertain, but probably similar to Jupiter's, mostly hydrogen and helium, with some heavier elements mixed in. It might have a rocky core, surrounded by layers of metallic hydrogen, and then a thick atmosphere. Clouds probably form at various altitudes where different materials condense, perhaps silicate clouds, iron clouds, or other exotic cloud types similar to those found on hot Jupiters but at different temperatures due to this object's lower temperature. The weather on this world would be strange. With no star to create a day divided by night temperature difference, there's no hot side and cool side to drive atmospheric circulation. Instead, weather patterns would be driven by the object's internal heat escaping, by its rotation, which we don't know, but which probably makes it complete one rotation every 5 to 10 hours, typical for Jupiter mass objects, and by possible chemical reactions in the atmosphere. The weather might be more symmetric and less dramatic than on planets with strong stellar heating. The discovery of this and other rogue planets has profound implications. If rogue planets are common, as some theories suggest, they could outnumber stars in the galaxy. That would mean there are hundreds of billions or even trillions of these orphan worlds drifting through the Milky Way, most of them cold and dark, invisible to our telescopes. Some might be gas giants like this one. Others might be rocky worlds, Earth-sized or even smaller, frozen solid and traveling alone through the darkness. Some of these rogue planets might pass relatively close to our solar system. There have been occasional suggestions that Planet 9, a hypothetical planet in the outer solar system invoked to explain certain orbital anomalies, might actually be a captured rogue planet that wandered too close to the Sun and was captured by its gravity. This scenario is considered unlikely by most astronomers, but it's not impossible. The rogue planet also raises philosophical questions about the definition of planet. If we define planets as objects that orbit stars, this isn't a planet. But it has planetary mass, probably formed through planetary processes or something similar, and has many characteristics we associate with planets. The International Astronomical Union, which officially defines astronomical terms, doesn't have a clear definition for rogue planets. They're in a sort of limbo, not quite planets by the strictest definition, not quite brown dwarfs despite their similarities. And out there in the darkness, this orphan world continues its lonely journey through the galaxy. It has no sunrise, no seasons, no companion worlds. It travels through the space between stars, following its own trajectory around the galactic center, taking about 250 million years to complete one orbit around the galaxy, just as our Sun does. It will never return to whatever system birthed it. It will wander alone for billions of years, gradually cooling, fading, until it becomes just another dark, cold object drifting through the void, undetectable and invisible, a ghost world in the darkness. From a world with no star, we move to one that barely seems connected to its stars, a planet whose very existence challenges everything we thought we knew about orbital mechanics. Sometimes, astronomy reveals objects that seem to violate the rules we thought we understood. This planet is one such case, a world with an orbit so peculiar, so unexpected, that scientists have struggled to explain how it could exist. HD 106906b orbits at an immense distance from its host star, in a configuration that by all rights shouldn't be stable, yet there it is, defying our theoretical predictions and forcing us to reconsider our models of planetary system formation. The planet orbits a binary star system about 336 light-years from Earth. The two stars orbit each other closely, and the planet orbits both stars at a distance of roughly 738 astronomical units. That's 738 times the distance from Earth to the Sun, or about 68 billion miles. To put this in perspective, Neptune, the most distant planet in our solar system, orbits at about 30 astronomical units. Pluto, at its farthest, reaches about 49 astronomical units. This planet orbits 15 times farther from its stars than Pluto does from the Sunday. At this distance, the gravitational bond between the planet and its stars is extraordinarily weak. The stars exert only a feeble gravitational pull on the planet, barely enough to keep it bound. Any nearby passing star could easily disrupt the orbit, either pulling the planet away entirely or perturbing its orbit significantly. The orbit is also tilted. It doesn't lie in the same plane as the disk of debris and smaller bodies orbiting the binary stars, but instead is inclined at a steep angle. This is very unusual for planets, which typically form in the protoplanetary disk and therefore orbit in the same plane as the disk. The planet's mass is about 11 times Jupiter's mass, placing it near the boundary between planet and brown dwarf. Its estimated temperature is around 2,700 degrees Fahrenheit, hot enough to glow visibly with its own heat, like the rogue planet we discussed earlier. This heat is left over from the planet's formation. At its current vast distance from the stars, it receives almost no heat from them. How did this planet end up in such a bizarre orbit? Scientists have proposed several possibilities, none of them entirely satisfactory. One scenario suggests the planet formed much closer to the stars, perhaps at a distance of a few to 10 astronomical units, where conditions for planet formation are more favorable. Through gravitational interactions with other planets or material in the system, it could have been scattered outward onto a highly elongated orbit. Over time, interactions with the remnant disk of gas and debris might have circularized this orbit somewhat, leaving the planet in its current configuration. The planet's very existence at this location challenges our understanding of planetary system stability. Typically, orbits at such large distances are thought to be unstable over the lifetime of the system. Random perturbations from passing stars, from the gravitational influence of the galactic disk, or from other factors, would gradually alter the orbit until the planet either falls back toward the stars or is ejected into interstellar space entirely. The fact that this planet still exists in this orbit suggests either that the system is younger than we think and the planet hasn't had time to be disrupted yet, or that there's some stabilizing mechanism we don't fully understand. Interestingly, this system has been compared to our own solar system's hypothetical Planet 9. For years, astronomers have noticed that certain distant objects in the outer solar system have orbits that seem to be influenced by something massive we haven't yet found. One explanation is that there's a large planet, perhaps 5 to 10 times Earth's mass, orbiting the Sun at a distance of several hundred astronomical units in a region we've barely explored. If Planet 9 exists, it would have some similarities to this planet, orbiting very far from its star, with an orbit tilted relative to the plane of the other planets, posing similar questions about how it ended up there. The comparison to Planet 9 isn't exact. The hypothetical Planet 9 would be much less massive and orbit somewhat closer to the Sun than this Jupiter-mass planet orbits its binary stars, but the basic puzzle is the same. How do you get massive objects into such distant, peculiar orbits? The fact that we found at least one clear example of such an object in another system suggests that whatever mechanism creates these configurations might not be as rare as we thought. The planet's isolation has one significant benefit. It's relatively easy to observe directly. Most exoplanets are impossible to image directly because they're so close to their bright host stars that the star's glare overwhelms any light from the planet. But this planet orbits so far from its stars that it's well separated in the sky, allowing astronomers to take actual pictures of it. These direct images have allowed scientists to study the planet's atmosphere through spectroscopy, analyzing the light it emits to determine its composition and temperature. These observations have revealed that the planet's atmosphere likely contains water vapor, carbon monoxide, and possibly other molecules. The presence of carbon monoxide is particularly interesting because it suggests the atmosphere is carbon-rich compared to oxygen, which might tell us something about where and how the planet formed. The ratio of carbon to oxygen in a planet's atmosphere can be a clue to its formation, location, because different regions of the protoplanetary disk have different carbon to oxygen ratios depending on temperature and which materials have condensed into solids versus remaining as gas. The planet glows in infrared wavelengths from its own heat, making it relatively bright despite its enormous distance from its stars. Over millions and billions of years, it will gradually cool, becoming fainter in the infrared until it's eventually too dim to see with current telescopes. But for now, while it's still young and hot, it offers a valuable opportunity to study a massive planet's atmosphere in detail. What would it be like on this planet? The stars would appear as two bright points of light in the sky, close together but clearly separate. Combined, they would appear only about as bright as the full moon appears from Earth, providing illumination, certainly, but not much warmth and not much light by daytime standards. The sky would be full of stars, much like Earth's night sky, with no single dominant sun to wash them out. Shadows would be soft and diffuse, cast by two suns whose light combines. The planet almost certainly has a system of moons most giant planets do, and if you stood on one of those moons, protected from the heat and gravity, of course, you would see the planet looming huge in your sky, with the two distant stars providing dim illumination. The planet would probably show cloud bands like Jupiter's, driven by its internal heat and rapid rotation. The whole scene would be one of isolation and cold beauty, a far-flung outpost of the planetary system, barely held by the star's gravity, orbiting once every 15,000 years or so. The planet's future is uncertain. It might remain in its current orbit for billions of years, gradually cooling but otherwise unchanged. Or it might be ejected by a passing star sometime in the next few million or billion years, becoming a rogue planet like the Orphan we discussed earlier. Or, in the unimaginably distant future, when the stars themselves die, the planet might escape during the chaos of stellar evolution, flung out to wander the galaxy alone. For now, it remains a puzzle and a wonder. A planet that shouldn't exist in the orbit it occupies, yet undeniably there, observed and studied and photographed. It challenges our theories, forces us to expand our thinking about what's possible, and reminds us that nature is under no obligation to make sense according to our current understanding. The universe contains not just the planets we expected, but also the planets we never imagined, in orbits we thought impossible, existing in defiance of our predictions. And perhaps that's the most important lesson from all these bizarre worlds. The universe is more creative, more diverse, more strange and wonderful than our theories can fully capture. For every rule we think we've established, there's an exception waiting to be found. For every "this is how planets must be," there's a planet saying "not necessarily." The impossible orbit planet is just one more example of this principle, one more reminder that exploration and discovery will always reveal surprises, that our understanding is always provisional and incomplete, and that the cosmos will never run out of ways to astonish us. For our final stop, we visit Kepler 10c, a planet that broke one of the most fundamental rules we thought governed planetary formation. We thought we understood how massive rocky planets could be. According to our theories, there was an upper limit to the size of terrestrial planets, planets made primarily of rock and metal rather than gas. Beyond a certain mass, perhaps 10 times Earth's mass, a planet would start accumulating huge amounts of hydrogen and helium from the surrounding protoplanetary disk, transforming into a gas giant like Jupiter or Neptune rather than remaining rocky. This seemed like a fundamental limit, a boundary nature shouldn't cross. Then we discovered this planet, and it broke the rules completely. The planet orbits a sun-like star about 560 light-years from Earth, completing each orbit in 45 days. It's about 2.3 times Earth's diameter, which doesn't sound dramatic. We've found many super-Earths with similar sizes. But the mass measurements revealed something shocking. The planet weighs approximately 17 times as much as Earth. That's far more massive than any rocky planet should be, according to our models. It's 3 times more massive than the theoretical upper limit for rocky planets to remain rocky. When scientists first calculated the planet's density from its mass and size, they found it to be about 7.5 grams per cubic centimeter denser than Earth, which averages 5.5 grams per cubic centimeter, and comparable to the density of iron. This high density proved that the planet couldn't be a gas giant or even a mini Neptune with a thick hydrogen atmosphere. It had to be made of rock, metal, or other high-density materials. It was a true rocky planet, just far more massive than anyone thought possible. The discovery was announced as a mega-Earth, a rocky planet so massive it challenged our understanding of planet formation. Scientists were shocked. How could a planet accumulate so much rock and metal without also capturing enormous amounts of gas? The conventional wisdom was that once a rocky core reached about 10 Earth masses, its gravity became strong enough to rapidly accumulate gas from the surrounding disk, creating a thick hydrogen-helium envelope and transforming into a gas giant. This planet somehow avoided that fate despite being 17 Earth masses. Even if the mass is slightly lower than 17 Earth masses, the planet remains extraordinarily massive for a rocky world. And its existence has profound implications for our understanding of planet formation and planetary diversity. If rocky planets can be this massive, there might be a whole category of mega-Earths out there that we didn't expect, planets that are rocky like Earth, but far more massive, with surface gravities strong enough to crush any visitor, with geological processes driven by heat and pressure, unlike anything in our solar system. What would conditions be like on such a world? The surface gravity would be immense, roughly 3 times Earth's gravity, meaning that if you weigh 150 pounds on Earth, you'd weigh about 450 pounds on this planet. Standing would be difficult. Walking would be exhausting. Your body would feel compressed under its own weight. Any building or structure would need to be far stronger than Earth equivalents to avoid being crushed. Mountains couldn't rise as high because the rock itself would flow under the extreme pressure, limiting the maximum height of surface features. The planet orbits fairly close to its star, at a distance similar to Mercury's orbit around the Sunday. The star is somewhat smaller and cooler than our Sun, but the planet still receives substantial radiation, heating its surface to temperatures around 500 to 600 degrees Fahrenheit, far too hot for liquid water, too hot for life as we know it. Likely showing one perpetual day side and a frozen night side, extreme temperature differences exist between them. With 17 times Earth's mass packed into only about 2.3 times Earth's radius, the planet's interior would be under enormous pressure. The pressure at the core could be 10 times higher than at Earth's core, possibly creating exotic phases of rock and iron that don't exist on Earth. At these pressures, materials behave differently, they become more compressible, thermal properties change, and new crystal structures become stable. The geological activity on such a world would be intense. The enormous mass means enormous gravitational potential energy, and any internal heat from radioactive decay or residual formation heat would drive powerful convection in the mantle. Plate tectonics, if they exist, might operate differently than on Earth, perhaps with thicker, stronger plates due to the higher gravity and pressure. Volcanic activity could be more energetic, with magma erupting under high pressure, potentially creating explosive events far more powerful than any on Earth. The atmosphere, if it exists, would be compressed by the high gravity into a thin layer hugging the surface. Air pressure at the surface could be much higher than on Earth, even with a similar total amount of atmosphere, because the high gravity would compact everything downward. This might create weather patterns different from Earth's, with powerful winds driven by the temperature difference between day and night sides, but constrained to a thin atmospheric shell by the intense gravity. Could such a world support life? The high gravity would be a challenge, but life is adaptable. On Earth, organisms exist in high-pressure environments, like the deep ocean, and they've evolved structures to withstand those pressures. Life on a mega-Earth might evolve to be low to the ground, with strong support structures, perhaps more similar to plants or fungi than to animals. The high surface temperature makes this particular mega-Earth uninhabitable, but other mega-Earths in cooler orbits might be habitable, though life there would face challenges we don't encounter on Earth. The discovery of this massive rocky planet has changed how we think about planetary populations. Before its discovery, we thought there was a desert in the size distribution few or no planets between about 10 Earth masses and gas giant sizes like Neptune. This planet fills that gap, suggesting that massive rocky planets might be more common than we thought. Since its discovery, other candidates for mega-Earths have been found, though confirming their rocky composition is difficult. These mega-Earths might be important for understanding planetary system architecture. If massive rocky planets can form, they might affect the formation and migration of other planets in the system. They could act as gravitational barriers, preventing material from migrating inward or outward, or they could scatter smaller planets onto different orbits. Understanding their formation and prevalence helps us understand how planetary systems evolve. The mega-Earth also raises questions about habitability. We've focused much of our search for life on planets similar in size to Earth, assuming that super-Earths, much larger than our planet, would be uninhabitable due to their thick atmospheres and high gravity. But if rocky mega-Earths exist in habitable zones around their stars, we might need to reconsider. Perhaps life could adapt to high gravity. Perhaps these massive worlds could maintain stable climates over billions of years, giving life time to evolve. Perhaps the high gravity, rather than being a barrier, could actually help retain atmospheres and oceans, preventing them from being stripped away by stellar winds. For now, the mega-Earth orbits its ancient star, its surface baking under stellar radiation, its interior compressed to densities and pressures we can only estimate, a monument to nature's ability to surprise us. It's a planet that shouldn't exist, according to our theories of the 1992 and early 2000s, yet undeniably real, observed and measured and confirmed. It's expanded our understanding of what planets can be, how massive rocky worlds can grow, and how diverse the planetary population truly is. We've journeyed across the galaxy, visiting worlds that seem torn from imagination rather than reality. Glass rains sideways at hypersonic speeds. Diamonds form planet-sized spheres. Darkness deeper than coal absorbs nearly all light. Iron falls as rain from metal clouds. Twin suns set over alien horizons. Temperatures rival the surfaces of stars. Ice remains frozen solid at temperatures hot enough to melt lead. Planets are devoured by their stars. Orphan worlds drift alone through the darkness. Each of these worlds teaches us something profound. The universe is not constrained by our expectations. The comfortable environment we enjoy on Earth is an exception, not the rule. Most planets are hostile beyond imagination, existing under conditions so extreme that they challenge our understanding of physics, chemistry, and planetary science. 50 years ago, we knew of only 9 planets in our solar system. We assumed other systems would be similar. We were spectacularly wrong. The first exoplanets discovered hot Jupiters orbiting closer to their stars than Mercury shouldn't have existed, according to our theories. With each new discovery, we've had to refine our understanding, sometimes making small adjustments, sometimes completely overturning previous assumptions. Now, with thousands of confirmed exoplanets, we're beginning to understand the true diversity of planetary systems. But we've barely scratched the surface. The next generation of telescopes will revolutionize our understanding, characterizing atmospheres, imaging planets directly, and undoubtedly finding new categories of bizarre worlds we haven't imagined yet. That's the nature of exploration and discovery. Each answer generates new questions. We thought we understood planets, and then we discovered gas giants orbiting closer to their stars than Mercury. We thought we knew planetary atmospheres, and then we found worlds with glass rain and ruby clouds. We thought planets needed stars, and then we found rogues drifting alone. These bizarre planets are out there right now, orbiting their stars or drifting alone, each one a natural experiment in extreme physics, each one a reminder that the universe is richer and stranger than our wildest science fiction. And perhaps most remarkably, we found them. Humans, confined to a single planet, used our intelligence and instruments to discover worlds light years away, to measure their properties, to understand their nature. We stand at the beginning of the age of planetary exploration. Future generations will know far more than we do. But we are the generation that made the discoveries, that first realized how strange and varied planets could be. The glass rains on, the iron falls, the diamonds spin, the double suns set, the orphans drift, and we watch and measure and marvel. The universe is full of bizarre planets that shouldn't exist, but they do, and that makes all the difference.